simulation. So in this scenario, we have a robot which is starting at a point 0, 0 in an infinite xy plane, which means it can move pretty much infinitely across this plane, and there are a sequence of commands that you can receive. So you receive a -2 command, you turn left 90 degrees. So let's say if you are facing north, then you go west. But let's say if you're facing south, then you'd go east. And -1 is another command, and if you get that command, you turn to the right. So if you're at north and you get -1 command, you turn to the east. And if you're at south and you get a -1 command, you go to the west. And you also, another command that's possible is k, which is between 1 and 9 units. So you can move forward k units in your current direction. So let's say if you are at the north direction, you move north by k units. If you're at the south direction, you move south by k units. So we notice that we need to keep track of the direction that you're moving in at all times. Some of the grid squares in the infinite xy plane are obstacles, so we cannot be on the same position as where these obstacles are. We are given an array of obstacles in which each element is a tuple of x and y. X is the x coordinate of the obstacle and y is the y coordinate of the obstacle. So let's say if we run into an obstacle in our movement, we will instead stay in the current location and we will continue on to the next command. The final task is to return the maximum Euclidean distance that the robot can get from the origin. So since we're starting it from 0, 0, this is kind of simple to do, as we can just square the x coordinate and the y coordinates and sum it up. So let's look at an example grid. So as we can see here, we have our robot at index 2, 3, and we have obstacles which are seen as stars here. The robot can move in 4 directions, both north, south, east and west. Let's look through an example movement. So here we start off at 0, 0, and let's say if we receive a k that lets us move forward, we will end up in this position. And let's say we receive another command, which in this case is going to be -1, so we turn to the right, so north becomes east and we face right, as seen in this example. Then let's say we receive another command, we go to the right by 1 step. Let's say k is 1 here, and then we receive another command which is -1, so we turn to the right one more time and we face south. And we also receive a k of 3 and we move 3 steps down. The next command, we get a command of -2 and we now move from south to east. And let's say if you get a k of 9, you realize that it's not possible to go all the way, as there is a star in the second last column of the grid. So we stop right before the star. So to find the maximum distance at each new position, we need to do this. We need to update maximum distance to be the maximum between maximum distance and x coordinate squared plus the y coordinate squared. One approach that we could do is keep track of all the directional changes that we need and simulate the entire process. To watch out for the obstacles, we can store each obstacle in a set to allow for O1 lookup time and move 1 step at a time as we iterate O through k, and we stop if the next place to move has already been occupied. The max distance will have the same formula as you can see here. However, we need to realize, do we really need to move 1 step at a time? Even though k is 9, what if k is a large number in another kind of question? What if the maximum steps you can move at each operation is 10,000? Is it really very practical to move 1 step at a time? Or is a better, more efficient method possible? If we know exactly where the obstacles lie, we won't need to simulate movement 1 space at a time. So from here, the robot's k is 9, So by right it can move a maximum of k steps to the right. However, realize that when it tries to move to its fourth step, there's an obstacle, so it has to stop at the third step to the right. So we can naturally stop one space before the obstacle and proceed on to the next command. So here is the approach to solve this problem. We need to store the rows and columns of obstacles that have been present in the grid. How do we do that? Dictionaries. So here we can set up two dictionaries. One is column dictionary, which stores the obstacles based on the y coordinates, and we also have row dictionary, which stores obstacles with the key as the x coordinates. So for every obstacle that we have, we set r equals to I of 0 and c equals to I of 1, and then we pretty much perform a simple dictionary update. So at the end of the update of the dictionaries, if we look at calls dict, for every key, which is for every column, you would have a list of rows that are all obstacles. This will allow us to identify if any vertical column or horizontal column in the grid has any obstacles or not. So we also need to set up a directional array. As mentioned earlier, it's very important for us to keep track of directions that we move. So we can set up an array and set it such that 0 is north, 1 is east, 2 is south, and 3 is west. And initially, as stated in the question, we set our starting direction to be directions 0, which is going to be north. And then now this is how we update the directions. Let's say if the command is -2, so which means we need to go to the left, we simply update direction to be direction -1. For example, in this case, let's say if we are at south, we will move the index back by one, so you go from 2 to 1. If we are at 0, you'll set it up to be -1, which will become the last element in the directions array, which will be 3, so we will go west from north. Also, if we are moving to the right, which is in the case when the command is -1, we simply have to do the modulo operation, and directions will become direction plus 1 modulo 4. For example, let's say if you want to move from west to north, which is moving a right operation, we pretty much have to add 1 to the index and then divide it by 4, and the remainder is going to be 0. So now the direction is north. So how do we perform the obstacle direction and stop ahead? So we can notice that the upper limit of movement this is a case where we're moving upwards in a column, right? So the upper limit of the movement is going to be x and y plus k. K is the maximum steps you can move between 1 and 9 in the question. If there is an obstacle that is between xy and xy plus k, if the obstacle is at xz, then the end position is going to be xz minus 1 as we stop one step before the obstacle. Z is thus the lowest possible position between y and y plus k. It has to be the lowest position, as the first obstacle we see will pretty much stop the operation. So that's why we need to maintain that z is the lowest position possible. So here is the approach. I will show you how it works for one direction, and we can see how it works for other directions as well. So if the direction is 0, which is we are moving north, we check for obstacles in the current vertical column. So that's what we can do if R enrolls DCT, which is a O1 operation in the dictionary. And we set the initial closest obstacle y coordinate, and we initially set it to be start 1, which is the y coordinate of the current start point, plus the command, which is k plus 1, right? and then we get a list which is the value in the dictionary for that row. So our LST will contain all the y coordinates of obstacles in this vertical column. You need to note that not all of these y coordinates are going to be within our range of the current start and the maximum possible start. So for each element that we have in the list, we need to check that if the element is indeed started is lesser than the initial start y value plus k, which is command, as if the obstacle is beyond our range of motion, then it's not really that relevant to us. We also need to ensure that this element is greater than our start y value, as it is possible for obstacles to be below our robot's position. So in that case, it's not really relevant to us, as it's not going to stop our movement in any way. And we set mx to be the minimum between mx and lm. So this ensures, as we have discussed previously, is to make sure that we stop at the lowest possible point, at the lowest possible obstacle in our path of motion. Then, if mx ends up being lesser than or equal to start 1 plus command, which means the obstacle is in our direction of motion and is somewhere in the middle, we set our new final position just before the obstacle. So start was our xy coordinate array, so we set start to be start 0 and mx minus 1. So the final position is set just before the obstacle. Otherwise, if it's not lesser than or equal to start 1 plus command, we will know that there are no valid obstacles in the path till y plus k. There could be obstacles below y, but it's not relevant to us, as it's not obstructing our path of motion. So if there's no valid obstacle, then we can just move all the way. The other case is in the case that there are no obstacles in this vertical column at all, so that there is no need for us to restrict our range of motion in this vertical column. So in that case, we just set start to be start 0, and then the y coordinate is going to be start 1 plus command. So we can do a similar process for moving to the east, to the south, and to the west. Note that for the south and west, it's pretty much very similar, except that the signs are different to match for moving left and down. So that's the only difference. Conceptually, it's pretty much the same. And we also need to update our max distance and at the end of each movement that we see in the grid, and we return match result, which will be the result of our analysis. So that is the end of today's question. Thanks for watching.